Okay, so we are going to look at some example problems for conservation of momentum. So if you recall, we talked about three different types of collisions that you guys are going to need to understand how to solve for. Basically, we have elastic and inelastic. Those are the main categories. So elastic collisions, we have our objects are going to collide, and then we're going to have them move so that they have independent velocities, so they move separately. Then we have inelastic collisions where our objects are going to collide, but then they are going to stick together. So they are going to move with the same common velocity because they are now moving as if they were one object. Okay, so those are the two main categories. So elastic and inelastic. So in perfectly inelastic collisions, we have both conservation. In elastic collisions, we have both conservation of momentum and conservation of energy. With perfectly inelastic, we do have conservation of momentum. We always have conservation of momentum, but we would not have conservation of energy. Okay, so our kinetic energy value would change. And if we just kind of think, very basic, there was some sort of deformation, there was some sort of energy needed in order to mesh or join those two objects together. Okay, so without getting into too much deep thought, that's kind of the gist of what we need to understand there. Then we talked about recoil or explosion collisions, which are really just kind of a reverse of what we would traditionally see with our perfectly inelastic collisions. So these are the three categories that we discussed in the notes. So what we're going to do is just work through some example problems. Again, my focus is more about showing you how to set up the problem and how to organize your math work. I'm not concerned so much today with executing the algebra itself with all the numbers plugged in. At this point, you should be capable of doing that step. It's really more about just giving you some ideas as to how to set up your math work, how to illustrate or not illustrate, how you're going to organize your variables, and make sure that you use the correct equation here. Okay, so if we look at the formulas, I have two different equations, and it just kind of depends on what type of collision we have, and that's going to determine what our formula should look like. Okay. All right, so for our first example, we have a 300 kilogram truck, and it is driving, not 300, 3,000, and it is driving to the east with a speed of 10 meters per second. He collides with a 1,000 kilogram car that is at rest. So then they are going to collide. After the collision, the car has a velocity of 15 meters per second in the same direction. So here's my car. Its mass has not changed, and it has a velocity of 15 meters per second in the same direction as the truck that was moving initially. Okay, so it's going to be a positive 15 or continue moving to the right. What is the truck's final velocity? So from this story, we can see that my objects stayed separate. They moved separately. They gave me the velocity of the car. They asked for the velocity of the truck. So that would imply that they're not the same. I did give you a picture here just to kind of help you visually understand what is happening, but I'm also demonstrating that as I read through the word problem, I can create my own picture. The benefit to putting your illustration together, number one, if for many of you, is going to help you to kind of process what is happening so that you comprehend the storyline, and that will help kind of guide your math work, because you'll understand better what is supposed to be happening with these values. But it also gives you a designated spot for each of your objects. Now we're going to have an object 1 and an object 2. And for each of those, we're going to have a mass and a velocity. And for each of those, we're going to have an initial and a final velocity. So there's lots of different variables happening here. We want to make sure that we keep everything organized and we pair all of our information up correctly. So by creating an illustration, you now have a spot for each of your objects, both before and after. And I think it just comes out to be very convenient when it comes time to, number one, build your equation. You may be able to recognize that it's elastic or inelastic, and you may know exactly which equation to use just because you've identified the type of collision. But you can also use the illustration that you've created to kind of show you what that formula should look like. So in this particular question, here is my M1V1, here is my M2V2. Now I understand that the masses are not changing in the before and after, so you could choose not to write your mass before and after, but I'm going to choose to do so, at least in this first example, so that you could see here's my M1, my V1 is what I'm looking for, and again this side is the final side of my illustration, and then here's my M2, V2. So my formula is M1V1 initial plus M2V2 initial equals M1V1 final plus M2V2 final. And so I look at my picture, I've got 4 different boxes, 4 different momentums, right? My initials are all on the left, my finals are all on the right. My truck in this case was object 1, and my car is object 2. So when it's time for me to substitute in, now it's much easier for me to not only plug my numbers in, but I don't really have to put much thought into how the numbers should be paired up. I don't have to worry about, oh, I didn't realize that this was the velocity for this object. Everything's already just kind of put together. So it makes it for a very easy substitution step, which easy is always a good thing. Okay, so when we plug our numbers in, we should see that this car initially had a velocity of 0. It had no momentum. So either in the writing the equation step or in the substitution step, you should recognize that we have a momentum of 0 for our car. So this whole thing just becomes a value of 0. So I have 3,000 times 10 equals 3,000 times VF plus 1,000 times 15. So you can plug your numbers in first here, like I did. I realize that majority of my students prefer to plug their numbers in first. Or you could do your algebra first. Once again, those 2 choices should not make a difference in the value that you calculate. So from here, I would need to subtract over my 15,000. And then I would take my new value over here and simply divide by my mass, okay? When I complete this calculation, I should end up with a final velocity that is positive. And this final velocity is going to be less than the speed of the truck initially. So if I just stop and think using my common sense, yes, it makes sense. The truck had more momentum, so he is going to continue moving in the direction that he was originally moving, but he crashes, he experiences a force that is applied against his motion, so he's going to experience an impulse or a change in momentum so that his speed has decreased. So we end up with a value less than what we started with at the beginning of the story. All right, here's another example. We have a 6 kilogram car, and it is rolling to the right with a velocity of 2 meters per second. A second cart with a mass of 4 kilograms is moving at 10 meters per second to the left. Remember, velocity is a vector, so you must list this as a negative 10. Then they're going to collide. After the collision, the 4 kilogram cart has a velocity of 2.6 meters per second to the right, so it stays positive. What is the speed and direction of the 6 kilogram cart? All right, so now we have a question. What is the speed and the direction of the 6 kilogram cart? So this velocity is what they are asking us to solve for, okay? So we have m1 v1 initial plus m2 v2 initial equals m1 v1 final minus m2 v2 final. In this case, nothing is going to cancel out. All of my objects have velocities both before and after, so I'm going to need to put all these numbers in. For this question, we're solving for this final velocity. So whether you choose to plug your numbers in first or do your algebra first, ultimately we're going to have to subtract this information over to the other side. And I would recommend, if you can, go ahead and do your algebra, because what this does for us is it allows us to plug these numbers in exactly the way they were given to us in the story. So if you're listing your givens, then that shouldn't be a problem. But it also allows me to calculate this much more quickly than if I had plugged in my numbers first and done all of these calculations separately, written them down, and then plug them into this. So ideally, you can go ahead and move your numbers over so that you're just plugging it all into the calculator at one time. After we do this, we're going to need to divide by the mass of m1, which ends up being dividing by 6. So we're really going to have to just plug this into the calculator, and that's going to give me my final velocity. After we finish this calculation, we find that our final velocity comes out to be a negative 0.40. And this is going to be measured in meters per second because it is a velocity. So what this is saying here, that the 6 kilogram object is going to bounce so that it moves in the opposite direction from its original motion with a new velocity of 6 meters per second. All right, perfectly inelastic. Here we have a situation where at some point my objects are connected. We may see it where our objects start off separate and then they get joined together, or we may be given an example where our objects start off joined together and then there's some sort of explosion or recoil force experienced that causes the objects to move in opposite directions. So we have our grandma with a mass of 80 kilograms, and she is skating, and she is going to collide with a kid with a mass of 40 kilograms. What is their velocity after the collision? So VF is what we are looking for. Now, should we have a VF1 or a V1F and a V2F, or is it just VF? In this case, it should just be one single VF. There's no need to identify a first or second object because they are going to stick together. So how can I know that from the reading? From the reading, it says what is their velocity, implying that we have a situation where they have the same velocities, which is asking for the one. It says in the written problem that they're going to collide inelastically, and then in this particular case, the question goes with the picture. So you can see from the picture that the velocity of grandma is 6 meters per second, and the velocity of the boy is 0. Once again, they told us that he had a velocity of 0. And these would be their initials. And we are looking for the final. So I have M1 V1 initial plus M2 V2 initial. And then over here, they stick together so that we only have one final velocity. Here, my second object is initially at rest. So I just have M1 V1 initial equals M1 plus M2. So now we're solving for our final velocity. Sorry, that was supposed to be a VF, not a V1. So we're solving for our final velocity here. So we're going to take 80 times 6, and we're going to set that equal to the sum of our masses. So we're dividing both sides by 120, okay? When we finish this calculation, we get 4.0 meters per second, 4.0 meters per second, and this is going to represent the final velocity of my joined grandma and the kid. Now this question also asks how much kinetic energy is lost. Remember, in perfectly inelastic collisions, we have a change in our kinetic energy. So here we're going to say change in kinetic energy is KE final minus KE initial. So if you recall, the formula for kinetic energy is simply 1/2 mv squared minus 1/2 mv squared Okay, so now we have, sorry about that, that's not what I want to do, just get off the Zoom, there we go. So now we have, let's put those things back, 1/2 mv squared initial. So what we would do here is we would simply take our initial kinetic energy, which initially it was only grandma who had any kind of velocity. So this initial kinetic energy is going to come from our grandma. Our final kinetic energy is going to be from grandma and the kid, but remember they joined up together to give us one velocity. So grandma and the kid goes here, and we would just find the difference between the two. Okay, for our last example, we have a situation here where we have an astronaut who was originally at rest. And this astronaut is attached somehow, some way, holding on to or connected to somehow a thruster that contains gas that's going to expel some gas. So it says they're initially at rest. They give us the mass of the astronaut. And they tell us that gas is going to be expelled at some velocity. What is the velocity of the astronaut after firing the thruster? So initially the astronaut has no velocity. Afterwards, the astronaut's going to have some velocity, and they tell us that the gas inside of the thruster is going to have a velocity of 875 meters per second, and we have a mass of, this says 35 grams, so we're going to convert that to kilograms. And then what we need to understand is that the gas also initially had a velocity of 0. It wasn't moving until it got fired, right? So the initial velocity for the gas is also going to be 0, but I am going to draw this so that the astronaut and then the thruster that he is connected to that contains the gas, that they are connected. So collectively they have one velocity, okay? So here we would say the mass of the astronaut plus the mass of the gas are combined, and together they have one initial velocity, equals the mass and velocity on the final side plus the mass and velocity final. All right, so in this case, the entire first half, the before or the initial side of the equation equals 0. So this entire thing is going to give me a value of 0. Now, you may be wondering, how can I have a total momentum of 0? But remember, these two objects are in contact with each other. They are in contact with each other. So when they make that contact, the gas exerts a force onto the astronaut exerts a force onto the gas. The forces are equal in magnitude, but opposite in direction. They are applying a force because of contact, so therefore their times are the same, so their changes in momentum are the same, okay? So here I have a total momentum of 0, and we talked before about how this impulse is going to cause some sort of change in momentum, and this impulse is going to cause a change in momentum, and those magnitudes are going to be the same, but because momentum is a vector, one will be a positive change in momentum and the other will be a negative. So this means that their magnitudes are the same, but because one's positive, one's negative, they mathematically add up to 0. When we do our algebra here, in this particular question, we are solving for this velocity. So mathematically, I'm going to ultimately subtract this over. What I want to show you is that this cancels out over here on the right. All right, so now we have our relationship set up where we have negative mv mv of our second object equals to a positive magnitude of mv of our first object. Now here, what we are trying to show you is that their momentums are the same, but one is expressed as a positive value and the other is expressed as a negative value. And this is true because of Newton's third law: equal forces, opposite directions, same changes in momentum, opposite directions. They both were initially at rest, therefore the change in momentum that they experience will also represent their final momentums. When you plug your numbers into this calculation, please do not overthink it and try to do any kind of extra changing of signs because they are in the opposite direction. When we subtracted our second momentum over and we expressed it now with a negative m2 v2, that has already accounted for the fact that it's an opposite direction. Okay, so for this question, whenever we get ready to plug in our numbers, we have a negative 0.035 times 875, I'm not going and inserting an additional negative there, equals 84 times VF. And so we would simply take this and we would divide by our 84. And what that's going to do is that's going to calculate for us a negative number for my velocity. But if I think about this conceptually, that is completely acceptable. If I identified the direction of the gas to be a positive velocity here, then it makes sense that my astronaut goes in the opposite direction, so his velocity should be a negative. So this question, you should calculate a negative velocity of 0.36 meters